Hi, AP Bio. So today our video lesson is going to be on biological molecules, but we're going to start with sort of a basic introduction to atoms, because in order to understand molecules, we first have to understand atoms. So when we think about atoms and we think about elements, we commonly think of a couple of big ticket elements, right? And these are going to be the four essential elements that make up 96% of all living matter. So these are going to be oxygen, carbon, nitrogen, and hydrogen. You're familiar with these when you think about things like water, carbon dioxide, CO2, nitrogen, ammonium. All of those things contain these four essential elements. These are some common examples, right? Coal is made of carbon primarily, and it can be compressed and turned into diamonds. Nitrogen is used in a lot of fertilizers, as well as the hydrogen bomb. If you've watched the most recent movies coming out, then you will have been familiar with hydrogen bombs. And then this oxygen one is a little bit different, but in places where pollution is a big concern, they actually have started selling pure oxygen and advertising it as helping with things like energy and recovery, and travel and things like that. So these are some of the ways that you might have seen these biological elements in the past. Now, trace elements are essential elements that are still required by an organism to survive, but only in smaller quantities. So if 96% of life is essential elements, then the other 4% of life is going to be made of a lot of calcium, phosphorus, potassium, and sodium. These elements typically come in the form of ions. Now, keep in mind that word ion. We're going to talk about what an ion is in just a second. But before we dive into what an ion is, we first need to understand what an element actually is. When I talk about trace elements and essential elements, what am I actually talking about? Well, I'm talking about atoms, and atoms are going to be the smallest particle that anything can be broken into and still retain common characteristics. So this is a common model of an atom that I have on the screen. And I want you to think about these two questions. We're thinking about the element of carbon, right? Carbon as in carbon dioxide or as in coal or diamonds. What makes a carbon atom different from a hydrogen atom? They're elements, they're atoms. What makes them different from each other? And when we're thinking about these atoms, what causes them to form chemical bonds? What causes them to stick together? When we get water, when we get H2O, what causes H and O, hydrogen and oxygen, to stick together? What causes carbon and oxygen in carbon dioxide that you are breathing out? What causes those things to stick together? Well, elements are defined by the number of protons in the nucleus, right? And again, this is hopefully review from your chemistry classes. This is not expected to be a first introduction to the idea of atoms and bonds. So if you need to review some of this terminology, go back to some of the chemistry videos and review some of the chemistry videos, because this is specifically focusing on biology for chemistry, right? So elements are defined by the number of protons in the nucleus, and the number of protons and electrons are usually the same, unless you're talking about an ion. We're going to talk about ions in a second. In biology, we are typically interested in the electrons outside of the nucleus, because these are what go through chemical bonds. So let's take a look at what this actually looks like. This is a great video. I'm not going to show this for the sake of copyright, but it's a great visualization of what atoms really look like, because these electrons that we're talking about here in the orbitals outside of the nucleus, they are not actually found in orbitals. They're found in these sort of cloud-like structures. So visualizing what those electron clouds actually look like has been a difficult concept, but they've been able to do it using mathematical models. And this video has a really great visualization of that. I encourage you to go find that video. It's called What Atoms Really Look Like. Now, each orbital can only house a certain number of electrons. So if we go back to our model, this is the model of an atom. And each of these little dotted circles represents a possible electron that atom can hold in that orbital. Now, most atoms will attempt to fulfill what's called the octet rule. The octet rule states that atoms will attempt to become energetically more stable by finding an electron for their lowest unfilled electron shell. So in this atom, right, we're looking at an atom that has one electron in its first orbital. Now, we're not going to worry about S and P orbitals. You don't need to worry about that for AP Bio. But we're looking in the first orbital. Now, this first orbital is weird because it technically only has 2 electrons. So the octet rule does not necessarily apply to this first orbital because it only has 2 electrons. And if we were to draw these in, if we were to say, how many electrons will this atom need to complete its octet rule? Well, it would need 1 atom. And again, I know this is confusing because octet makes you think 8. But for the first orbital, there's only 2 electrons. So in order to fulfill its octet rule, it would only need 1 electron. Let's take a look at another example. So this atom has its first 2 electrons in that first orbital. They are present. It also has 4 electrons in the second orbital. So how many electrons does this atom need to complete its octet rule? Did you figure it out? This atom is going to need 1, 2, 3, 4. So the yellow dotted circles are going to represent possible electrons that this atom will want to fulfill its electron orbitals in order to become more stable. That's the goal of all atoms, right? They are trying to make friends so that they can stabilize and ground themselves into a more stable chemical state, right? So when we're talking about atoms and we're talking about that outermost orbital, we're talking about valence electrons. Now, be careful because the term valence number and valence electrons often get confused. Valence number is the number of missing electrons from the atom, right? So this is also the number of bonds that it can make. The number of missing electrons is also the number of bonds that it can make. Valence electrons are the number of electrons that an atom has in its outermost orbital. So I want you to take a second and see if you can draw these atoms. I'm going to draw and show you the first one in just a second, but I want you to see if you can do it on your own. Were you able to figure it out? This one's a little tricky. This would require a little bit more chemistry background knowledge. So let's take a look. So the first atom that I gave you was hydrogen. Now, hydrogen is interesting because it only has 1 electron in its outermost orbital. So it has a valence of 1. This means that it only wants to make 1 bond. It's only missing 1 electron. So it's going to try to make 1 bond. Let's do the same thing with oxygen. Oxygen has a valence of 2, but oxygen has fulfilled its its innermost electron shell. So that means that those 2 electrons, they're happy. They're good to go. They are sort of stable. But the outermost electron shell, the outermost orbital, has 6 electrons in it. So oxygen, because it only has 6 electrons of the 8 total that it's trying to get, it's going to have a valence of 2, meaning that it wants to have 2 electrons. It wants to have 2 bonds that are going to stabilize it. Now that we've done this for hydrogen and oxygen, see if you can do nitrogen and carbon, if you weren't already able to do this in the first place. Try to draw the structures based on their valence number. And then if you would like, you can also do the Lewis dot structure at the bottom. Did you get it? Hopefully you paused the video and tried it out. This is what those 2 atoms are going to look like. And you notice these are also our big 4 essential elements. These are the big kahunas of AP Bio. These are the atoms you are going to hear us talk about over and over and over again. So don't forget these guys, okay? Carbon is going to have a valence of 4, meaning it wants to make 4 bonds. Nitrogen is going to have a valence of 3, meaning it's going to want to make 3 bonds. Now, things get kind of interesting because even though this is sort of the basics of these atoms, things can get kind of interesting when it comes to bonding. Let's pause for a second and see if you can do some practice problems. See if you can answer these questions on your own. Pause the video and try to answer these questions on your own. Did you get it? All right. Check your answers. See how you were able to do. Now, number 1, how many valence electrons does carbon have? It has 4 electrons. How many bonds can carbon make? It can make 4 bonds. Phosphorus has 5 valence electrons. How many bonds can phosphorus make? Well, it can make 3 bonds because it's missing 3 electrons. Now, draw the valence shell for phosphorus. Well, here's our valence shell for phosphorus. Phosphorus has the innermost electron orbital filled. It's got the second innermost electron orbital filled, and it also has 5 electrons in that third orbital, meaning that it wants to make 3 bonds. And that can be seen here in number 5. Phosphorus has been bonded to 3 chlorine atoms. Hopefully that was helpful for you. And we are going to get into bonding in the next video. Hopefully that was helpful.